So this is with connection establishment. So what do you think of connection termination? You think this is easy? Well, there are always twists and turns with respect to networking protocols. So this also has a twist. Before I get there, let's spend a little bit of time on understanding what connection termination is. Suppose process A is talking with process B and process A thinks it is done, so it is going to issue the close call. So this asymmetric release means you are now going to just shut down the socket, thereby preventing not only sending of the data but also receiving of the data from the other end. So in telephone analogy, this is like you're talking on the phone. You think you are done, so you just bang the phone down, even when the other person still wants to talk with you. This is no good. This leads to loss of data, not only of data that is in transit, but also if B still has some data to send, if you close the connection, you're going to miss out on this data. So what is desired is this symmetric release where you treat each connection as two separate unidirectional connections and each side has to be released separately. So in other words, in this particular case, when process A says closed, you will not be sending any more data, but you will still listen to data that is coming from the B side. And this symmetric release is a tricky business. So let me motivate this through this two-army problem. This is a very famous problem that is posed in the context of distributed systems. There is the blue army and then there is the red army, which is the enemy of this blue army. Now this blue army is split. One battalion is on top of one hill, the other battalion is on top of another hill, and this enemy is in the valley. So this enemy is rather large, so this attack from the blue army will succeed only if and only if both of them attack the enemy at the same time. If only one of them attacks, they'll get butchered. And here is the problem. Both Army 1 and Army 2 need to decide on when to attack this red army, for which they need to communicate, and the messenger who is going to communicate has to go through the valley to deliver this message to Army 2, and there is a danger that this messenger could be captured by this particular enemy. So what strategy should they adopt to ensure that they both attack the red army at the same time? So think about it. Well, there is no solution to this problem. Let me explain. Suppose this blue army sent a message, let me call it message 1, that says let's attack on Sunday at 9 a.m. After sending this message, do you think this army 1 can just go ahead and attack the red army on Sunday at 9 a.m.? No, right? What if this message was lost? In other words, that messenger got captured. Then army 1 would get butchered. So what it should do is when it is sending this message, it can say, please act. Let's suppose this message got through. Now this army 2 is going to say, okay, fine, let's attack. And it sent this particular message. Now, do you think Army 2 can just go ahead and attack this red army on Sunday at 9 a.m.? Definitely not. What if this message got lost? It knows that Army 1 will attack only after it receives this particular message because it asked for an acknowledgement. So Army 2 needs an acknowledgement from Army 1. So it can just also say, please act. Now let's say Army 1 received this particular message and it is saying, okay, fine, I received your message. This is an acknowledgement. Now does this mean Army 1 can just go ahead and attack? Well, no, because what if this message got lost? It knows that Army 2 will attack only if this message reached it fine. Now you see what is happening? No matter how many messages you exchange, you cannot decide on when to attack. So what is its relevance to connection termination? Here it is. So if neither side is ready to disconnect, unless it is sure that the other side is ready to disconnect will never happen. So this is a bit of a paradox. You really need to spend some time thinking about it to convince yourself that this is what is happening. So what is the solution then? Well, human lives are really not at stake here. While this is an unsolvable problem, you just follow a simple approach and make do with the consequences. So this is what happens in the implementation. So both sides follow a simple two-way handshake where if this process set close, it sends a finish packet, and once this acknowledgement comes, this side is no more going to send data, and similarly this side could continue sending data for some time, and when that particular process says close, you're going to send a fin which is going to acknowledge, and this connection, this side of the connection is also closed. By the way, in this process, you do take care through timeouts that you do retransmit the fin or the ACK so that this connection closes. But after a few number of retries, if it's still you're not able to get through, you're just going to close the connection. So this figure captures the TCP state diagram. It looks a bit complex, but it is really not. In this state diagram, this portion corresponds to the connection establishment and this portion corresponds to the connection termination. Another point to note is this blue line which is being shown here represents the server path, and this red line which is shown here represents the client path. So let's see what is happening. So both of them start with the closed state. The server starts listen, so that is why it now starts to listen, whereas the client connects to the server, so it calls the connect function. As a consequence of this connect function, the SYN packets get sent. So this representation where x/y, x is the cause, this is the response. So as a consequence of this, the server is now in the listen state and the client is in the SYN send state. Now when the server is listening, it is going to get a SYN packet. As a consequence of this, it is going to send the SYN plus ACK packet. So this comes when the client is in the SYN send state. So as a consequence of this, receiving the SYN plus ACK, it is going to send an ACK packet. From the client side, the three-way handshake has finished, so it is now going to get into the established connection state. And once this ACK reaches the server, it is also going to move from the SYN receive to the established state. Once the connection is established, the data exchange begins. So this is where the sliding window protocol comes into play. We will see more of this later. Now if the client were to close the connection, so this issues the close command. As a consequence of this, the fin packet gets sent and the client is now going to go to this fin wait 1 state. And the server, when it receives this fin packet, it is going to acknowledge that particular packet and it is going to go to close wait state. Now once this ACK has come, this is here, the client is now gone to fin wait 2 state. So effectively the client side connection has closed at this particular stage because the client is in this fin wait stage. Now still data exchange can potentially happen. Once the server issues the close command, then the server as a consequence of this is going to send the fin packet. So this fin arrives here at the client and as a consequence of this, the client is going to send the ACK. Once this ACK comes, it's not listed here. So this is the ACK. The server is also going to go to the closed connection. A point to note here is the client is not going to directly jump to the close. It is going to wait in this special state called time wait. So basically when you are terminating a connection, before you fully terminate the particular connection, that is go to the closed state, one side is going to wait in this time wait state. The reason for this, I'll get to it shortly. By the way, this state diagram doesn't capture all cases, and what I have shown via the blue and the red lines is the typical scenario. There are other transitions also as indicated here which can also be followed. I will leave it as an exercise for you to go through other transitions. So what is this time wait state? Basically, when you open a connection, after opening the connection, you are going to exchange data. So this is the data phase, and then you're going to terminate the connection. The use of time wait state is before you close the connection and thereby reuse the port numbers, you will wait in this time wait state for twice the maximum segment lifetime so that you can clear out all the older packets in the network and thereby preventing them from interfering with the new connection. So for example, you opened a connection, let me call this connection 1, between some source, destination, source, these are IP, and source port and the destination port. And you exchange some data, and let's say there is no time wait state. So as soon as you receive the FIN from the other side and send an acknowledgement, you have just closed the connection. Now some of this data belonging to this connection could still be in the network because it was retransmitted or whatever. Now let's say the same endpoints corresponding to this reopen a new connection called connection 2 with the same bit. So this connection 2 is between the same source and destination and with the same source port and the destination port. Now if you don't wait for this time, what can happen is this older data can come as part of this connection 2, and this connection 2, typically the sequence numbers of that will not match this particular sequence number. As a consequence of this, you're going to abort this connection by sending the reset flag. So this is unnecessary work. So to prevent this particular case, as part of connection 1 itself, you wait in this time wait state till all this data disappears. Only then you free up that particular socket and the ports, thereby the second connection can be established. So when you're waiting in this time wait state, even if at the application layer you try to reopen the connection with this 4 tuple, you will get that bind failed. So this was mentioned as part of the socket programming tutorial also. Now, how much time to wait in this time wait state is an implementation artifact. It can range from 30 seconds to 2 minutes. You can set it to a small value as well, but then you have to face this consequence of older packets interfering with the new connection. So there is this neat little command called netstat that lets you check the status of the connections, both TCP as well as UDP, and the state the TCP connection is in. So let's try that. So it is netstat -a lists out all the connections. Let me start out the regular netstat. So as you can see, one of these connections, which is to this 161 address, is in the time wait state, while as the others here are in established state. So if I do -a, it's going to list lot more. These are local processes. They're all in the listening state. I have one in the time wait state, some more in the time wait state now. Some are in the established state, some are in the listening state, and this also lists the UDP connections that are active on my computer. This refers to the IPv6 address. So there are some processes that are using the IPv6 address space. This you see as part of the TCP also. So here is the IPv6 address space. So to summarize, TCP is a connection oriented protocol. This connection management is complicated by the fact that we are running over a best effort service model. We saw a specific problem arising out of these duplicates interfering with the new connection. We handle this via the three-way handshake. Making use of random initial sequence numbers also helps in this context. Connection termination is also a complex problem, but we went with a simple approach where we managed termination via a two-way handshake. We also looked at the TCP state diagram. Up ahead, we will see the sliding window in action in the established state.